okay, up to this point. So this initially is a quadratically increasing, and then it is linearly increasing up to this point. Now, what is the velocity after 4 seconds? Yeah, the displacement after 4 seconds. This is 1. Okay, again, I agree. This is wrong. This is just 1 meter. So this is 1 meter, and then another 2 seconds with 1 meter per second. So end up with here on the top with 3 meters. This is this position. Now, what happens later on is the velocity still continues to increase, and then decreases with 1 meter per second squared t prime squared. So, sorry, I'm a bit off. Let's say if this would be the starting point, so it will decrease and then it goes down. Therefore, maybe I plot this one once more. So initially we have quadratically increasing function, then it continues to go linearly increase. We know now this one is 3, this is 1, this is 0, this is s of t, and from this point on let's see what happens after. So this continues to increase, and then we get a quadratic going. So what is S3 after 1 second? That is would be then after S3 after 5 seconds. So after 1 second, that is this distance from here to here. This is 1 meter minus, and here is 1 meter squared. Okay, 1 minus 1 meter, so that is 0. So what it does, it increases and then it goes down. So this was the graph initially. This is quadratic, this goes with t squared, is proportional to t squared. This part is proportionally to t, and this part goes with proportionally to minus t squared. And here's a bend over. So the maximum displacement is reached shortly after, between 4 and 5, for the velocity diagram. Just to discuss a bit more, I plot now on the below again the velocity diagram. Initially the velocity was linearly increasing, then it was constant, and then it went down from 1 to minus 1 meter per second, the velocity. And here this is displacement, is measured in meters. This was 2, and this was 4, and this was 5. So during a linear increase of the velocity, we have a quadratic increase in the displacement. That is comes from the fact that the curve, the area under the curve, which is proportional to displacement, is quadratically increasing. During that time, the area is linearly increasing. Here, linear is a linear increase for a constant velocity. Constant velocity, you get a linear increase. Then it decreases the velocity, and we are here from this point to here we have a negative, and though it's not a parabola, but now it's otherwise formed. The parabola is with the highest point pointing downwards, and somehow this velocity still increases, and the maximum velocity is, the maximum displacement is obtained when the velocity has reached is still positive, so, or it just goes through zero. Here still the velocity increases, that's why here still the displacement increases. Once the velocity goes negative, the displacement also decreases. And if we continue, let's say continue for a longer time, finally we will cross the zero line, and that maybe could be an exercise for you to calculate at what time you actually reach a zero velocity again, zero displacement again. Okay, just to remember, if we have a constant increasing, a linearly increasing velocity, we have a displacement which goes quadratically, and we have an acceleration which is constant and positive. If it is linearly decreasing velocity, we have a constant negative acceleration, and the acceleration is zero when the velocity is not changing. The definitions for the displacement given as a velocity is v of t prime dt prime, and then we integrate from 0 to t. This is our displacement. The acceleration is the derivative dv dt. V is a function of t. This concludes this example, and I hope you understand now the relationship between displacement, velocity, and acceleration.